శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ 2008 లో స్థాపించిన కళాశాలలో NBA, NAC A గ్రేడ్ మరియు ISO సర్టిఫికేషన్ సాధించిన మొట్టమొదటి కళాశాల శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ త్వరలో అటానమస్ కాబోతోంది.
2014లో ISO గుర్తింపు, 2015లో రాష్ట్ర ప్రభుత్వంచే A గ్రేడ్, 2016లో NAC A గ్రేడ్, ఇప్పుడు NBA సాధించిన సంస్థ శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ.
Good morning, students. So in the last class we have studied about some of the applications of our operational amplifier. So we have studied about a differentiator, integrator, voltage to current converter, as well as current to voltage converter. So these four topics we have covered in our last class, and now in this today's class we are going to discuss about the logarithmic amplifier, how our operational amplifier is going to perform. Good morning, students. So today we are going to discuss about logarithmic amplifier, or how our operational amplifier is going to behave as a logarithmic amplifier, and how the op amp is going to behave as an anti-logarithmic amplifier. So in the last classes, so we have discussed about the differentiator, integrator. So that is, differentiator is nothing but the op amp is going to produce the output voltage which is proportional to the differentiation of input voltage, which is equal to the differentiation of the input voltage. Coming to integration, there we have studied about the op amp, how the op amp is going to produce the integration of the input voltage, and here the output is nothing but integral of the input voltage. And the next application is how this op amp is going to convert output input voltage to output current. That is nothing but the changes in the input voltage must be able to change the output current, such that the output current must be proportional to the input voltage. So that we have seen in voltage to current converter. So, and we have observed that output voltage is proportional to the, so output current I naught is proportional to the input voltage. Nothing but here R1 is constant, so I naught is proportional to the input voltage variations. As input voltage is going to change, the I naught is going to change. And this circuit is also called as transconductance amplifier, and we have called this circuit as a transconductance amplifier. Next we have discussed about the current to voltage converter, in which here we are going to give the input current to the operational amplifier, so such that it is going to produce the output voltage which is proportional to the input current variations. So here, by seeing this output, you can observe that input current II is equal to V naught by RF. V naught by RF. From this equation, we can say that input current is proportional to output voltage, where RF is a constant value, and this circuit is also called as trans resistance amplifier. So Up to there we have completed in our last class, and today we are going to discuss about the next four applications of our operational amplifier. So that is, first of all, we are going to discuss about the comparator. Comparator. What is a comparator? The comparator is a circuit which compares nothing but two inputs. So where one of the input is a fixed value and another input is a time variable signal. So that fixed value, we are calling that fixed value signal as a reference voltage. And then the variable signal which we are applying when the output of this comparator produces when the input voltage, that is the signal what we have applied, is going to pass, that is going to coincide with the reference voltage, so here the one thing we have to remember that in this the op amp, in this application, the op amp is working as a open loop configuration. The op amp is working in open loop configuration, not in closed loop configuration. So up to now what we have discussed, in those applications the op amp is going to work in a closed loop configuration. Why closed loop we are going to tell means, because the feedback path is provided for an operational amplifier through from output to input, whereas in this comparator applications, the op amp is going to operate in open loop configuration. That means there will be no feedback in this application, and based upon this comparator applications, there will be two types. Nothing but our op amp is having two input terminals, that is a non-inverting terminal as well as inverting terminal. So if you give the input signal to inverting terminal, then it is called as inverting comparator. If you give our input signal to non-inverting terminal, then it is said to be non-inverting comparator. So there are two types, that is inverting and non-inverting comparators. So first we are going to discuss about the inverting comparator. So see here the operational amplifier. So where the input signal Vi is applied to the inverting terminal of op amp, and the supply voltages have been given, and output we are going to take at the output pin of operational amplifier, whereas the other input terminal, that is the other input terminal, is nothing but the reference voltage. So this will be set by the user itself, or else we can make it ground also. So when coming to the operation of this op amp, so when the input voltage exceeds this reference voltage, then the op amp is going to change its output. Okay, so we know that when op amp is going to operate in a open loop configuration, the op amp is going to operate in saturation region, not in linear region. That means the operational amplifier is going to switch between that is plus saturation, positive saturation region, as well as a negative saturation region. So that positive saturation region is going to depend upon the positive voltage applied to the operational amplifier, and negative saturation region is going to depend upon negative supply voltage given to the operational amplifier. So in this way, our op amp is going to produce the positive, is going to fluctuate. The output of op amp is going to change between these two values, plus vset and minus vset. So first of all, we are going to discuss about the inverting comparator of operational amplifier. So this is the basic comparator circuit, inverting comparator circuit, where we are giving input to the vi, we where we are giving input to the inverting terminal, and the reference voltage is given to the non-inverting terminal. So here in this slide you can see that the output value is going to fluctuate between the two voltage levels, that is plus vsat and minus vsat. So and this is based on whenever input crosses the reference voltage. Whenever input is going to cross the reference voltage, then the output is going to change its state from plus vsat to minus vsat and vice versa. So how it is going to change its state? So see here. So if we take an inverting comparator, then the output value of an inverting comparator will be minus vsat. It is at minus vsat when vi is greater than the reference voltage. Nothing but the output will be in minus vsat when vi is greater than v reference. And then similarly, the output will be plus vsat when vi is less than v reference. That is the applied input voltage. Whenever the applied input voltage is greater than the reference voltage, then the output of the op amp stays in minus vsat. Whenever the input voltage is less than the reference voltage, then the output of this inverting comparator is going to stay at plus vsat. So in this way, it is going to produce the output between these two values, that is plus vsat and minus vsat. So let us see an example. So here in this example, we are considering input signal, that is a sinusoidal signal which is given to the inverting input terminal of operational amplifier. And non-inverting input terminal, you can see here, this is the inverting input terminal for which we are giving a sinusoidal input signal. And for non-inverting input terminal, so we have made this non-inverting input terminal to be grounded. And when we have given the input sinusoidal signal, you can observe here the sinusoidal signal is going to start from here. So it is going to change its path like this. The sinusoidal signal is going to change its path in this manner. So when it is going to change its path, when it is going to change its path, so see here, so the sinusoidal signal is going to change from here and up to here, you can see. So this is during positive half cycle of the input signal. So as here the non-inverting terminal is grounded, we can say that the reference voltage is nothing but 0 volts. We can say that the reference voltage is nothing but the 0 volts. That means whenever the input signal is greater than 0 volts, as we have discussed now, whenever the input voltage is greater than 0 volts, then the op amp is going to stay, the op amp output is going to stay at minus vset. So this is what happening here. Whenever the input voltage is greater than 0, the op amp output is going to stay at a minus vset. And again, whenever the input voltage is less than 0, then at this point, so the op amp is going to change its state from a minus vsat to plus vsat. And again, whenever it is crossing 0, again the output of op amp is going to change its state. So here you can observe these changes in this waveform. So what we have observed mainly here, at a zero crossing of the signal, because why at zero crossing only the output is going to change? Because here the reference voltage, that is the voltage at a non-inverting terminal of op amp, the voltage at non-inverting terminal of op amp is grounded. So the reference voltage will be zero. The reference voltage will be zero. Hence, the output is going to change at a zero crossings of the signal. And we can call this circuit as a zero crossing detector. We can call this circuit also as a zero crossing detector. So this is about the inverting comparator of operational amplifier. So coming to another application, another comparator, that is non-inverting comparator. So here you can see in a non-inverting comparator, so there will be, in a non-inverting comparator, there will be, it will be same as inverting comparator. The difference is only the reference voltage here we are applying to non-inverting terminal, and input voltage we are going to apply to the, sorry, reference voltage we are applied to the inverting terminal, and input voltage we are applying to the non-inverting terminal of op amp. So hence when we are applying, that is nothing but we are going to give what we are going to give opposite to the inverting comparator. So we are going to change only the inputs. So where V reference is given to the inverting input, and input signal is given to the non-inverting comparator. So when we have changed this, we can observe that whenever the input voltage, so coming to the operation of this circuit, so whenever the input voltage is greater than the reference voltage, the output will be at plus Vsat. So in case of this non-inverting comparator, so it will be whenever the input voltage is greater than the reference voltage, the output stays at plus Vsat. So in case of non inverting, you can see the reverse operation. So whenever the input is greater than the reference voltage, the output will be minus Vsat there. But here, whenever the input is greater than the input reference voltage, then here the output will be at plus Vsat. And whenever the input is less than the reference voltage, the output will be minus Vsat. So in this way, the operational amplifier, that is, this is minus Vsat. So in this way, the op amp non-inverting comparator is going to produce the output between plus Vsat and minus Vsat. So if you observe an example, so here you can see, so the inverting terminal here is grounded, and we are giving the sinusoidal input to the non-inverting terminal of operational amplifier. So here you can observe the input sinusoidal wave, and in this circuit also we have taken the reference voltage as 0 volts. So whenever the input sinusoidal signal is going to cross 0 volts, then the op amp output is going to change its state. So see here, during positive half cycle of input signal, so as here the sinusoidal signal crosses 0, and Vi is greater than the reference voltage, that is reference voltage is 0 volts, then the output is going to stay at plus saturation voltage. And whenever Vi is less than Vi is less than the reference voltage, that is 0 volts, the output is going to stay at minus Vsat. So from this circuit, you can observe that during positive cycle of the sinusoidal wave, that is the input signal, the output is going to stay at plus Vsat. So as it is a non-inverting comparator, so the output will be positive when the input is positive. The output will be negative when it will be when the input is negative. So when in case of inverting, you can see that is invert. When input is positive, the output will be a negative Vsat. So this is nothing but invert. Inversion operation has been done here. So it is called inverting comparator. And in case of non-inverting comparator, so the output will be same, that is same polarity. So if vi is positive, the output is also stays at plus vsat. And here there is no linear relationship. So as op amp is going to operate in a open loop configuration, the gain will be very high. The open loop gain of op amp is very high, and op amp is going to operate in a saturation region. So that is how the output will be going to change between plus vsat and minus vsat. So these are the two comparators. These are the two comparators using operational amplifier. And coming to next application, so the op amp as a logarithmic amplifier. So here, how this op amp is going to perform the logarithmic amplifier. What is logarithmic amplifier? Why it is named as a logarithmic amplifier? Is nothing but here, nothing but the output, the output voltage produced by the op amp is proportional to the logarithmic logarithm of applied input voltage. Logarithmic value of the applied input voltage. So here, in case of this logarithmic amplifier, so how this logarithmic amplifier will be implemented by using this op amp means, here the non-inverting terminal of op amp is grounded, and here we are giving input to the inverting terminal through a resistor R1. And here you can see in this point, the op amp based logarithmic amplifier produces voltage at the output which is proportional to the logarithm of voltage applied to the resistor connected to its inverting terminal. So voltage applied to the inverting terminal through a resistor, through a resistor. And here the feedback is provided. Here you can see the feedback is provided with a PN junction diode, with a PN junction diode, such that the P terminal is connected to the inverting input, and N terminal, that is anode, is connected to the inverting input, and cathode is connected to the output of the operational amplifier. And feedback is provided here. The feedback is provided with the diode D, and the feedback current is flowing in this direction. So by using this circuit, we are going to produce an output which is proportional to the logarithm of input voltage. Logarithm of input voltage. So how it will be obtained, we are going to see now. So by writing the nodal equation at the inverting input terminal, by writing nodal equation at the inverting input terminal, we have here inverting input terminal. Here we are going to write the nodal equation. So as we know that as due to the virtual short concept or virtual ground concept, as the non-inverting terminal is grounded, we can say that the potential at this inverting terminal, at this node, is also zero. So when we are going to write the nodal equation, that is KCL, so then we can write a 0 minus Vi by R1. This is nothing but 0 minus Vi by R1 is nothing but current flowing through this resistor, and 0 minus V naught divided by this diode resistance we are going to consider. So here in the circuit itself, we are assuming that the current flowing through this diode is IF. So simply we are going to write, we are not writing 0 minus V naught divided by the resistance. So we are going to write simply as IF. So that is how the output equation will be 0 minus Vi divided by R1 plus IF is equal to 0. So from this equation, if you bring this Vi by R1 to right hand side, then it becomes, as it is negative, when we bring this to right hand side, it will become positive, and IF is equal to Vi by R1. So This is how we have obtained, and we are assuming this as equation 1. And now we are going to write the equation current uh, equation for the current that is flowing through the diode. So as diode is forward biased, it is having a forward resistance, and when diode is forward biased, we are going to write the current flowing through the diode. So as we know the diode current equation, that is I is equal to Is into e power Vf divided by eta Vt. So this is the equation for diode current equation as we have studied in our electronic devices and circuits subject. So from this equation, by using this equation, so in this equation, Is is nothing but the saturation current of the diode. So here If means forward current. That is when diode is forward biased, the current through the diode. And Is is the saturation current, and Vf is the voltage drop across the diode when it is forward biased. Okay. Next, Vt is the volt equivalent temperature. Volt equivalent temperature. So eta is equal to 1 or eta is equal to 2, and this eta depends upon uh, type of the semiconductor material. That is it may be a silicon or it may be a germanium. If it is silicon, that is equal to 1, and if it is germanium, that is equal to 2. And with this equation, so this is the diode forward current equation, and we are going to substitute this we are going to use this equation, this diode current equation. So where we are going to use this equation, so here you can see. Before going to that, we are going to write the KVL around the feedback loop of op amp. So when we are going to write the KVL around the feedback loop of op amp, so as we know that the voltage at the non-inverting terminal, sorry, the voltage at the inverting terminal is 0. The voltage at the inverting terminal is 0. Here the voltage at inverting terminal is 0. So we are going to write the KVL around this loop. So if you are going to write the KVL around that loop, so then 0 minus, so Vf is the forward voltage to the diode, minus output voltage V naught is equal to 0. So we can say that the Vf, the forward voltage of the diode, which is equal to minus V naught. The forward voltage of the diode, which is equal to minus V naught. So we are bringing this Vf to right hand side, then this will be Vf is equal to minus V naught. So substituting the value of Vf in equation 2. So we are going to substitute the value of Vf in the above equation, the current equation of the diode. So in the place of Vf, we are going to write this V naught minus V naught. So then this equation, that is If is equal to Is into e power, in the place of Vf, we are going to write V naught. So e power minus V naught divided by eta Vt. So this we are going to term as equation 3. So now equation 3, we can observe from this equation. So as we know that from the equation 1, so as we know that from the equation 1, If is equal to Vi by R1. If is equal to Vi by R1. So here in the place of If, we are going to write Vi by R1, which is equal to Is into e power minus V naught divided by eta Vt. By solving this equation, so we are going to get, we are bringing this Is to left hand side. So then this will be in the denominator section and is equal to e power the minus V naught divided by eta Vt. And by applying natural logarithm on both sides, we get ln of, that is natural logarithmic of this term is equal to this natural logarithm and this exponential term, that is e power, will be cancelled by this natural logarithmic term, and we are going to get minus V naught by eta Vt. So then we are going to get the output voltage V naught is equal to, finally the output voltage V naught is equal to minus eta Vt. We are bringing this eta Vt to this side and we are bringing this minus to this side. So minus eta Vt, natural logarithmic of input voltage. So here you can see as Eta Vt is volt equivalent temperatures, and that those terms are constant terms. Eta is a constant term, and Vt volt equivalent temperature is a constant term, and here R1 is also a constant term, and Is is also constant. Then we can say that V naught is proportional to natural logarithmic of changes in the input voltage. So the output voltage V naught will be a proportional to the natural logarithmic of input voltage for a fixed value of resistance R1. Hence, our op amp is going to perform its operation as a logarithmic amplifier. So in some textbooks, you can observe in the place of diode, there will be a transistor also, in which the base will be grounded. So no problem, you can write that. You can write that, or you can write this also. And next concept is op amp as a anti-logarithmic amplifier. Op amp as a anti-logarithmic amplifier. So as in case of logarithmic amplifier, it produces output voltage which is proportional to the logarithmic value of input voltage. Here it is going to produce, the op amp is going to produce output voltage which is anti-logarithmic value of input voltage, anti-log value of input voltage, anti-logarithmic value of input voltage. So here we are going to use the same diode, and in that circuit we have placed the diode in a feedback path, whereas in this circuit we are going to place the diode in directly. We are going to connect the diode to the inverting input terminal of op amp, and we are giving input to the diode. So here you can see, so here the diode which is connected between the input signal and the inverting input of operational amplifier, and here we are going to provide the feedback through resistor RF, and we are making the non-inverting terminal to be grounded. We are making the non-inverting terminal to be grounded, and hence when we are going to observe this, when we are going to see the output of this circuit. So for that, we are going to write the nodal equation here. So when we are going to write the nodal equation, as we know that due to virtual ground concept, if the non-inverting terminal is grounded, then we can say that the inverting terminal is also said to be grounded. So the voltage at this node will be also at zero volts, and hence we can write the equation, that is 0 minus Vi divided by the resistance in this path. As we have assumed that the current flowing through the diode is If, and from this node we are going to flow, we are going towards this direction, input direction, and when we are going in this path, the current coming opposite to us. So we can write the If as minus If. So minus If, that is KCL, Kirchhoff current law, we are going to write minus If plus 0 minus V naught divided by the resistance in this path. 0 minus V naught divided by resistance in this path. Here it is 0 minus V naught divided by resistance in this path will gives the current through this path, nothing but, is equal to 0. So from this equation we can write minus V naught by Rf is equal to If. So V naught is equal to If into Rf. So we are going to take this equation as equation number 4. And next, as we know that the diode current equation, If is equal to Is into e power eta with e power Vf divided by eta Vt. So Vf is the forward voltage of the diode, and we are going to substitute this value in place of If. So as we have written here, V naught is equal to minus Rf into If. In the place of If, we are going to write the diode current equation. So here we have substituted that value, diode current equation value, and then our output voltage is equal to minus Rf into If into e power Vf divided by eta Vt. So now we are going to write the Kirchhoff voltage law at the input side of the inverting terminal of the op amp. So then we can write, so where we are going to write this Kirchhoff voltage law at this, in this path, we are going to write. So Vi minus the voltage flowing, that is the voltage drop through the diode is nothing but the forward voltage, that is Vf. Vi minus Vf is equal to 0. So up to here. So Vi is Vf is equal to 0. So Vi is equal to Vf. So we can say that Vi is equal to Vf. So hence, by substituting that value, V naught is equal to minus Rf into Is e power Vi by eta Vt. So here, from this equation, we can observe that the output voltage is proportional to the anti-logarithmic value of, that is anti-natural logarithmic value of the input voltage for a fixed value of feedback resistor Rf. So this is how we are going to obtain, we are going to produce, we are going to produce the logarithmic value as well as anti-logarithmic value values by using our operational amplifier. And we have observed that how our operational amplifier is used as a logarithmic amplifier as well as anti-logarithmic amplifier. So with this, we will end this session. Thank you, students. Thank you, students.